Newton's first law of motion. Let's go over this again. I gave you the laws of motion, so now you need to think about it. So let's look. All right, so the first law of motion deals with inertia. Inertia is the tendency of an object to stay at rest or to stay in motion. So basically, this first law is stubborn. It's saying, I want to do what I want to do, and that's it. If I'm resting, I'm resting. The only way I could stop resting is if you make me. And the only way I'm going to stop moving is if you make me. So we know there are natural forces on the earth that make things change. That's friction. That's gravity. That could be a push force. That could be acceleration through electricity, through magnetism. All those forces that we talked about before we went on this crazy coronavirus break. Anyway, so this first law of motion has to do with balanced forces. Balanced forces keep things at rest. Balanced forces keep things in motion. So the minute the forces become unbalanced, that's when we have change. So Newton's first law of motion deals with balanced forces. An object will remain at rest or at constant speed unless it's acted upon by an unbalanced force. So they're saying right now everything is balanced, and the only way it's going to change is if we unbalance it. So the first law is pretty stubborn. So the assignment that I gave you the other day, I asked you to criticize or actually analyze the videos that I made. So the first one was the egg. So the egg was spinning, and I was spinning it, and then I stopped spinning it. But one of the eggs kept going, and the other one didn't. If you did a little Google research, you realize that's an oldest trick in the book. One of the eggs was hard-boiled, while the other one was not. The one that was hard-boiled is solid in the middle. So when I stopped it from going, it listened. It stopped. The other one was not hard-boiled. It had liquid inside. So when you spin it, the only thing I stopped was the shell. I can't get my fingers inside to stop the gooiness. So the gooey inside kept going. So even though it looked like I stopped it, I couldn't stop the inside. The only thing I could stop was the outside. So once it stopped, it kept spinning because the liquid on the inside kept going. An object wants to stay moving. So it didn't stop. This is a little boy, it's a test tube kid, on a skateboard hitting a rock. They both want to keep moving. The only thing that stopped was the skateboard. What stopped the skateboard is the rock. What happens to the test tube? It keeps going. Because it's stubborn. It doesn't want to change. It wants to keep going. And then plunk, it breaks. All right. Newton's first law of motion is inertia. An object will remain at rest or at constant speed unless acted upon by an unbalanced force. So what do we need to do? We need to look at examples of balanced forces. We need to look at examples of things that are at constant speed. So the most common example is the seatbelt. You're driving in a car 100 miles per hour. That's dangerous, but somebody stops short. The car stops. If you're not wearing a seatbelt, the person doesn't, because the only thing that's stopping is the car. The person is free to go, so you will go right out the windshield. You're going to wear a seatbelt. That's why they do so many tests on those test dummies, because you can't get hurt. So they're going to make sure that the seatbelt works, and they put an airbag there so that you get protected because you're going to go forward because you don't stop with the car. All right, there's so many examples. The most classic example I said is like the seatbelt example, but here's an example in the universe. An object in motion stays in motion. Our planet has been revolving around the sun for 4.6 billion years. Yes, billion. It doesn't stop because an object wants to stay moving, continue what it's doing. The only way it's going to stop is if something comes along and makes it stop. So that's why there's a lot of technology out there to check. Make sure that there's not an asteroid coming. We do know that our sun goes through a life cycle. So eventually in about another 5 billion years, it's going to expand a little bit. Maybe the pull of gravity will be greater and we get pulled in. That's 5 billion years from now. But right now, everything's balanced. So here we go around the sun. The planets in our solar system revolve because of inertia. This is Newton's first law. Balance. Everything's balanced, so it keeps going the same. Everything stays the same. You're either moving or you're stopped. So Newton's first law has to deal with inertia. So any example that you're going to use has to be with the law of gravity is something that's going to stop Newton's first law. But Newton's first law, you got to think about things. Is it balanced forces? Then it's going to stay doing the same thing. That's what Newton's first law is, inertia, either resting or going. All right, let me speed this up a little because we did all this already. So let's think about this. Which vehicle would be harder to move? Now we have two trucks, a big Mack truck and a small little car. So we know inertia has a concept that depends on mass. So if something's really big, are you going to move it good? No, it's going to be really difficult. This takes a lot of gas to move. It also takes a lot of gas to stop. So the big truck has a lot of inertia. It's going to take a lot of energy to move that truck. More mass, more inertia. The bigger the mass, the more inertia. Oh, there's another force. There's something else out there that Newton discovered that has mass. Concept of mass, gravity. The more mass, the greater the gravitational pull. So mass is a concept that really affects a lot of things in the universe. All right, let's go to Newton's second law of motion. Newton's second law of motion has to do with unbalanced forces. The first force was balanced, and now these are unbalanced. So Newton's second law says all right, so we had a little pause going on because I had to show the first grader her spelling words, but we're coming back. So let me get back to the PowerPoint. All right, no, not from the start. Current slide, please. All right, unbalanced forces show or cause acceleration or change in motion of an object. So first law of motion was all about balanced. The second law is an equation. This one's kind of easy because if they ask you, is this Newton's second law? You're looking for three things. Force equals mass times acceleration. The more force I put on it, the greater the acceleration. So now Baxter's not happy because I'm raising my voice. So Baxter says, please don't yell in my house. All right. The amount by which an object accelerates depends on the size of the force, the direction in which the force acts, and the mass of the object. So force equals mass times acceleration. The second law states that. I don't know what just happened. Let's go back. I don't know what I just did. There's something weird going on here. Force equals mass times acceleration. So here's Newton. Think about it. What does that actually mean? That means objects with more mass require more force to move than objects with less mass. Hold on one moment, please. So, two rocks are going to be dragged across the table. This is so obvious. Which one is easier to pull? Obviously the big one. Haha, just kidding. The little one is easier because it has less mass. So this is an easy concept. The bigger it is, the more force it's going to take. This goes with football. This goes with bowling. If you're a football player and you're not that tall or you're not that massive, how can you make up for it? You have to be really, really what? To knock down those people. You have to be really, really fast. So force requires two things, mass and speed. So when we throw a rock, if you just throw a rock into the pond, it doesn't make that much of a ripple. But if you throw with all your might, it's going to make a really big splash. So when you're jumping into the pool, the faster you jump into the pool, the bigger the splash. If you just slip in, you're not going to splash that much. So Newton's second law gives us the relationship between force, mass, and acceleration. Force equals mass times acceleration. I can give you a lot of examples, like bowling, for instance. You go in bowling with your family and you pick the 8-pound ball because you think you're cool. It's so light, so you're going to be able to throw that like a crazy maniac down the alley. If you don't throw it fast, that little 8-pound ball is not going to knock anything down. So most bowlers, and you hear them go when they hit every single pin, they're going to use a ball with some mass. Like professional bowlers probably use like a 16-pound ball. 16 pounds. That's double the ball that you picked up. I usually use like a 14-pound ball, maybe a 12-pound ball, and you want to give it enough speed because I have to force all those pins down. So you pick a good mass and you give it a good speed, a good pickup speed, and then you'll force the pins down because you can't touch all the pins, so the momentum is going to hit every single pin. One pin hits the next pin, etc. So if you don't have enough acceleration, those pins are not hitting each other. Just one pin just knocks over, doesn't knock the rest of them over. Even if you hit it smack in the middle, you only have to knock that first pin down and everything else is going to stay. All right. May the mass times the acceleration be with you. I think that was from Mr. Ferenzi because he likes that Star Wars stuff. All right. Newton's laws of motion. So what is the force here that's required for this dog to pull the sled? The mass of the sled is 50 kilograms. And the acceleration, he's trying to run 2 meters per second squared. So what do? You multiply. Force equals mass times acceleration. So mass is 50 and acceleration is 2. We multiply them together, we get 100. How much force does the dog need to accelerate the 50 kilogram sled at a rate of 2 meters per second squared? He needs the formula. Force equals mass times acceleration. We multiply it. You write it all out. So if we were in class, no naked numbers, and you need the formula, the substitution, and now the answer. What happened? I see kilograms, meters per second squared, and then the answer is newtons. Why? Because the unit for force is newtons. We forgot that. Remember we used spring scales? So it takes 100 newtons for the dog to pull the sled. Ta-da! All right, let's look at Newton's third law. Newton's third law of motion is, for every action, there's an equal and opposite reaction. Forces happen in pairs. If you want to walk, you have to push down so you can walk forward. Action force. It's the force acting in one direction. Reaction force is the force acting in another direction. Do you want to jump? Push down on the floor so you can jump up. Do you want to push your body forward in the pool? Well, you're going to push off the side of the pool, so you're going to push back to go forward. The guy's only walking because he's pushing down, and then his feet get pushed up. He looks like he's doing a little jig over here. Newton's third law allows us to walk. For every action, there is an equal and opposite reaction. Check out the boat. Jump off the boat. And what does the boat do? You're jumping forward and the boat moves backwards. You ever do that in the pool? You jump onto the tube. My mother used to hate us when we did this because I broke so many tubes doing this. And then if you didn't jump the right way, the tube would just go flying out from under you. The opposite direction. For every action, there is an equal and opposite reaction. Diving board. You jump down. You push down in order to go forward. For every action, there's an equal and opposite reaction. This is probably the example you're going to see all the time if you ever take a test on this. Rocket ship. In order for the rocket ship to go forward, all of the energy, the gases have to go down so the rocket ship can go up. So the action is the downward force of the gas. And the reaction, well, what does the rocket ship do? It goes forward. So Newton's third law is for every action, there's an equal and opposite reaction. Things work in pairs. One goes forward, the other one goes back. One goes to the side, the other one goes to the opposite side. So everything goes opposite. This dog. The rocket exerts a downward push on the exhausted gases. The gases push back by Newton's third law. All right, let's see. Oh, this is the best one. I wanted to do this in class. We would have so much fun. There's a lab that we would do. So you stick a balloon on a string, and then you put a straw on the string. So you put it through. Then you you take a string, you put a straw on it, then you tape the balloon onto it after you blow it up. So you blow up the balloon, but you don't tie it. You hold the edge. Then you tape it on to the string, and you watch the balloon go. And then you have to watch where the air goes. So the air rushes out the back, but the balloon goes up. You do this all the time. You put the balloon in your mouth. You blow it up. You let go. The balloon goes flying into the air. But what you don't realize is the air goes in the opposite direction. And that's because you can't see the air. So the same thing with Newton's cradle. You push this forward, it's going to push back. Everything is opposite. So let's look at these little examples right now, shall we? Birds flying. How does the bird go forward? it has to push its wings down and the air goes up. So everything goes opposite. So the action force is the wings get pushed down and then the air pushes back up so it can go fly. Swimming. They're going to push their little fins. When they push their fins forward or back, they push them back so that it's not going to be able to, so you push them back so it moves forward. Just like swimming. You put your arm forward and you pull the water back so you can go forward. So when we swim, we do the same thing that the fish do. So the action is the wing and the reaction is the air. The action is the fins going back and the reaction is the fish going forward. Okay, let's go over these really quickly. For every action, there's an equal and opposite reaction. Is that the first law, the second law, or the third law? For every action, there's an equal and opposite reaction. Which law is that? An object in motion will stay in motion, and an object at rest will stay at rest, unless acted upon by an unbalanced force. Which law is that? And then the last one, acceleration of an object depends on the force and the mass of an object. Let's put them in order. An object in motion stays in motion, does not belong there. It belongs there. It's balance forces. The first law is balance, so the only way we can change anything is making it unbalanced. So they might ask you, which law deals with balanced forces? That's the first law. Which law deals with unbalanced forces? Because we need to push something, acceleration. In order for anything to move, it has to be unbalanced, or in order for anything to change. So the acceleration of the object depends on the force and the mass. For reaction, there's an equal and opposite reaction is the third one. Good job. All right, so now this is what you would have done in class. You would have done a group activity, and you would have put them into 3 columns. So right now, I would like for you to do that. So there are examples, and you're going to put them into 3 different columns. So the examples are on your document. You're going to put all the first law in the first column, all of the second law in the second column, and all of the third law in the third column. Good luck. I love you guys and miss you so much. Bye-bye. Wait, how do I stop this? And I'm going to stop it now. Stop and save.